Hi, welcome back. This is the projectiles for number 4. We're going to solve or continue solving this problem which we have here. It is the cliff problem right here. So in the previous video we solved for time. So when we scroll down we'll find that, let's do that. There it is. Perfect. That this is our time right here. 7.62 seconds. And that's the total time it takes for the object to go this full distance from here to here like that. So in this next video, what I'm going to do is solve the rest of these. So the next question asks for range. So what I did is just, you can see, copy and pasted the same problem, made it a little bigger. Range refers to the x component, so that's the range. Now remember that the x coordinate only has one model of motion. So this is pretty nice because generally we do have Vx, and we happen to have that in the other problem. That's 51.91. We solved that already. I got it from, if you look back, Vx. So remember, we're not using the 65, we're using this number. So let's go forward. And we have velocity. Now, in order to find x, we need to know how long it took to get to where we're looking at. So we need how long it took to get from here to here. This happens to be coordinated with the total time. If we want x, the total range, we need the total time. Lucky for us, we already calculated that. That was in the previous problem. So having this is very valuable. This is how long it takes to go from here to here, which is the whole time. So x, as you can see, if I solve algebraically, it reduces down to something we can solve pretty simply by finding the velocity in the x, which we did, times the total time. Just like that. Now when I solve for this, let me grab my calculator. 7.62 times 51.91. Oops, hold on. Alright, so we get a pretty big range, but this seems logical because we have a very fast speed going on right here. And there we have it. That is the next section. What is the range? Okay, let's proceed to the next question. Next question says, what is the landing velocity? So this is complicated because remember, we no longer have just one velocity. We actually have two. We have the Vx and we have Vy. Because this thing's moving basically like this, right? Down and over. So the question's looking for this part of a triangle that we're going to make. Because we have two components of motion, just like we started with. We ended with the same type of idea. So, to find this, first of all, we're looking for V, which has both Vx and Vy. So that's just step one, something we should note there, that this is a combination of the two, not of one individually. 2, we need to find both Vx final and Vy final. But if you recall, this is constant. This value stays the same, which is really nice because we already have that value. So I'm just going to write it over here. We have Vx is 51.91 meters per second. And once again, where did we get that? That's this number right here. That stays the same throughout the whole trajectory. That says stay same. That's because there's nothing influencing it, because it's in the x direction. No gravity is going to account for that. But this is the one that we do have to pay attention to and calculate. So we need to use kinematics for this part. Alright, so let's do that. So I need to know the final velocity here, Vf final. So actually what I'm going to do is actually take the problem from this point here and call that my initial. So with the logic that I can do in the symmetry, I know that the initial here will be the same as over here, but negative. So the initial there was 21.06. So same thing right there. 21.06 will go right here. So there's an initial velocity. I have my displacement. So here we go. VI equals this, negative 21.06. My displacement is 125 meters down, so I'll throw in that negative right there. Sorry, it's floating, but it's part of this. Our acceleration is the same as all these problems, which makes our VF our unknown. So looking at my kinematic equations, this one is the best one. There we go. So I can plug in my information. So this is negative 21.06 squared plus 2a. I'm going to drop my units just so my stuff fits here, so I apologize for that. So let's calculate that. 21.06 squared plus 2 times 9.81 times 125 square root, oh, syntax error, gotta do it again. Alright, 21.06 squared plus 2, 9.81, 125 square root the answer to get just V by itself. Very good. Okay, V final, 53.81 meters per second. Down. Okay, and this is my Y. Alright, we're partially done because now we have an X and Y. So, in order to solve the official part, we got to figure out this angle. So, if you look at what our motion, the motion's doing, it's going over with a magnitude of 51 point, is it 91 or 19? 91, okay. 91 meters per second. And it is also falling, I'd like to do this visually. Let me rewrite this. I'll put this up here instead. So this is the X, the 51.91 meters per second. Now this is, and then the object's going down. This is the 53.81. So remember, this is the VY final. This is the VX. What I'm going to solve for is this dotted line. I want to know what V is. And I hope you recognize what you see here. This is a triangle, right triangle. So I'm basically solving a hypotenuse. And this is pretty safe to say. You can write this on your equation sheet, that this is true. I'm finding the hypotenuse by using the Pythagorean theorem. So 51.91 meters per second squared, meters per second squared after, plus the Y, so I'm going to solve that out. Great, so this becomes 74.77 meters per second. That's how fast this represents this number right here. Oops. So many sevens. I just added a 7. That's how fast it's striking the ground. And to get the direction, we got to get the angle. Now the angle I want is not this one down here, but the one, reference to the ground, right? Because how is it going into the ground? So I want this angle. Now that we have 3 sides of the triangle, you can use any sort of trig function to solve for this. But what I'm going to do is do tangent of the angle is equal to opposite over adjacent. So with that said, inverse tan of my opposite. So opposite this makes that the right value to put here. So that's the 81. And then the 51 goes underneath. Make sure you're in degree mode. Hours, you will not get the right answer. Very good, I'm in degree mode. Perfect, 46.03 degrees. So the official final answer would be the final velocity is equal to 74.77 meters per second at 46.03 degrees below horizontal. That is the official way to do this. So that was a pretty big chunk of that time, but that's what we figured out is the landing velocity. Alright, what do we have? Because we did the horizontal components, we did that already, we did that. The magnitude and velocity and the angle, good. Oh, we could do this. We could do this in our time. So maximum height. We got this. We could do this. Maximum height. That means, in addition to the 125, basically, how high did we go? So, we have that part already. That's 125. The question is basically, how high does this go? So we're looking for this small little piece. And once we have that, we're going to add it there. So it's this problem. Notice that I'm just taking and analyzing this section because this is the only part that we need. So, amongst the many different ways you can solve this, I'm going to use the fact that this is 0 and the y at the top. And that we have 21.06 here. Remember our Vy initial. So that would be my final. And looking for delta y. So, the equation I want to use for this will be the following. This one. You can see that I like this equation. It's great because I don't need time for this. That's what makes this one really nice. So I call this my final, my initial, delta y, and we have a, because a is acceleration. So, final 0, initial, positive because it's going up, plus 2. Now it's important that you make a down. You have to make a down. Otherwise this will not work. Because this sign makes this part negative, and that becomes negative. So it makes our delta y positive, which it should be because it's rising. So I guess I will show you. So 21.06 squared. If I move that over, I get negative 443.52 equals negative 19.6 delta y. So now we're going to do delta y, or solve for this. So 443.52 divided by 19.6. Solve for delta y. According to this, we got delta y positive, good. That means we went up. That's a good sign. And we have our, well, this is not the official end of the problem yet. We just found how high we went right here. This is the 22.63. Or in other words, this is this part right here. So to finish off that last question, the total or max displacement or height, it's going to be the 125 plus the 22.63 meters. Total height, 147.63 meters. And there you go. And that's the height of the ball, or whatever this thing was, I don't remember, of the object at the top right there. So this is a really good problem to study because it hits every major idea, concept, problem that I could ask about projectiles. So I definitely want to highlight this problem as a good one. Alright, I'll see you at the next video.